All right, so we're going to take a look at solving first-order differential equations. So we're actually going to solve the same basic first-order differential equation. We're just going to change the input characteristics. So for the first part, example 1a, so we're going to have 2y dot plus 10y. I have no input here, and so I just have an initial condition. So let's just solve that. All right, so the first thing we would do is we would convert this into a characteristic equation. I'll use lambda in this case, so it'd have 2 lambda plus 10. All right, lambda equals minus 5, so that says that's good. So that says the system's going to die out. E to the minus 5t is going to attenuate. All right, and then the complementary solution looks like follows. So for t equals 0, here we have that. We'd have c e to the minus 0, that becomes a 1, equals 6. So that's c equals 6. You've seen that before in math class. And so here's the response, 6 e to the minus 5t. Okay? And so we can analyze that. We have, here was the root, minus 5. We flip that, so that's 1/5 of that. Time constant is 1/5. Settling time, 4 time constants. So here's our initial condition. We just draw something that's attenuating in. There's room for artistic license here, folks. All right. We could have actually done this. Once we got this root, we could have said, oh, we know the initial condition, we know the root, we know the settling time, and you could have drawn this directly. All right. So now, and we'll note that if lambda had been minus 1, time constant would be 1, hence the settling time would be 4. If lambda were minus 10, the time constant would be 1/10, so the settling time would be 4/10. Everything just changes accordingly. And so we can start to analyze things. So let's take a look at this. We had our initial differential equation. If we have a root at minus 5, okay, we got this response. So let's notice, if we could take this and move it in this direction, okay, to say like minus 1, so that would have been moving it up here. What happens? Okay, notice the time constant goes to 1, settling time would go to 4. So as this root goes in this direction, things take longer to settle out. You know, that kind of makes sense, because if you cross this line and this becomes positive, now you'd have e to the positive and it would never die out. So as soon as this root here, or pole, or your eigenvalue, as soon as that goes to the positive side of this imaginary plane, time constant and settling time are all infinite. Okay? Never settles. So the closer you get to this imaginary axis, the longer it's taking to settle out. Okay? And then by the same token, as we go this way, like we said, if we let lambda equal 10, time constant is 1/10 and settling time is 4/10. As we go this way, it's settling faster and faster and faster. And this is something that's important. So when you go to take your controls course, you can look at a system, and based on where it's sitting here, you know, based on that real part, how long it's going to take to settle. And so from a controls point of view, you can say, where do I want to move it in terms of it being a better spot? So we move these things to get a response that we want. That's the principle of control. So finding these poles and moving them where we want them. Okay. And then there's some other factors, and we're going to get into that. All right. So we're going to go to our next one. So this one was just a pure initial condition response, right? So now we're going to do this again, except now we're just going to have a pure forced response. Okay, so here in this problem, we have a same basic differential equation, except now we have an input to u of t, where u of t is just, whenever you see u of t, it always means unit step input. What is a unit step input? It's 0 for all time less than 0. It's 1 from time equals 0 forward. So if you were to plot this point blank, it just looks like this. Here's 0, up, over. It's basically flipping a light switch. This is the light switch input. All right. So with that in mind, so if we look at this, and we should probably go back to this one page here, just a second while I bring it up. Where is it? Oh, here we are. Oops. So we want to form a particular solution. And it works out that it's this, but let's just kind of suss out where that comes from. All right. We have a unit step input. It's basically a 1. And then we look at this mess and go, how the heck does that go with that? Okay. Well, we'll note that a unit step input has no oscillation. So that means the omegas are 0. So sine of 0 is 0. So this term disappears. Cosine of 0 is 1. We don't have any e to the ht, so h is 0. E to the 0t is 1. So what I have left is I have a k of t term, all right? And so what is that? Okay, recall the input can be up to a to the m, blah, 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 up to this power. So I could have an input that either looks like a step, which would be t to the 0, or this can be a ramp, t. Well, it's a unit step. So that corresponds to this, k0t all by itself. That's all it is. It's just this by itself. Okay? So that means, we'll just go back into here. Here's our particular solution. And so what we get is, this is all it is. And so when you get your particular solution, you substitute it back into here. All right? This is just a constant. So 2 times the derivative of constant. What's that? Well, yp of dot is 0. The first derivative of the particular solution will be 0. All right? So now we insert all this into here, and we have 2, derivative of the particular solution is 0, plus 10, k, we want to figure out what that is, equals 2 times stick in the input. All right? That's 0. So we have 10k equals 2 times 1, or k equals 1/5 when you bring the 10 over. And so we're left with, so here's the particular solution, 1/5. So at steady state, when everything dies off, this is what's left. And there's a little mistake here, minus 5t. So notice when I said stuff dies off, c e to the minus 5t plus 1/5. This term is going to die off. This is the complementary solution. What does it do? It takes you from where you start, 0, and transitions you into your steady state. So this is a transient solution. Okay, it's taking you from one thing into another. So this is the complementary solution here. So we just apply it. So y of 0 equals 0. Stick that in. And then stick time equals 0 into this. So we have c e to the minus 5 times 0. Okay, that makes this term a 1 plus 1/5. All right, so c equals 1/5. Just solve for c. And then here's your final solution. Y of t is 1/5, 1 minus e to the minus 5t. We're all done. Okay, and we can plot that. Basic plot is a first order system. Okay, we know this dies off to 2% after 4/5 of a second. There's a 5 there, so time constant is 1/5, settling time 4/5. Here's this, the output is 1/5, so there's our plot. So let's look at another one. So now what we're going to do is we're going to look at this same problem. So look what we have now. We have 2 u of t, so there's the unit step input. The initial condition is 6. So this is basic, this third problem is the first two combined. No problem. So our input's the same, so our particular solution is k. The derivative of that's obviously 0. We substitute this in. 2 yp dot got the 0 plus 10k. We get 1/5. we're going to have the exact same steady state solution. All right. So now moving to the next step, we have some decisions of how we're going to apply this. All right. So I'm going to do this actually all in one shot. Okay. So once we get the particular solution, now we know we're going to, the forced response and the total solution can be both written this way. Y of t equals c e to the minus 5t plus 1/5. If we wanted to know the forced solution, I would then set y of 0 equal to 0, solve for that, and then I'd have to do the initial condition response and solve it and add that in. Okay, so let's just note this. If you wanted to solve this problem, you could have just done what we did in the first place. Solve for the initial condition, get that solution, that was our part A, get the forced response and add them together. And that would be the full response. Or we could just do it all at one time. So rather than, we're not going to set it to 0 this time, we're going to set it to the initial condition. Okay, y0 equals 6. Put time equal to 0 here. So you're left with c plus 1/5. Solve, you get c equals 5 4/5. And then here's the full solution. Okay, but we'll note we can rewrite this. Let's see what we have here. Okay, we solve for the full solution, but what I can do is split that into two parts. Here's the initial condition response. Here was our forced response we computed before. But notice something. 6 e to the minus 5t minus 1/5 e to the minus 5t gives you 5 4/5 e to the minus 5t. They are the same. So initial condition response, forced response, total response. And they simply add up. So we got one more to do in this video. So for this one, I'm going to go to the most complicated input we can have. So based on what we had in our method of undetermined coefficients, here this was, okay? Whatever this derivative is, the highest order derivative, that's the highest power we can have on our input. So, highest order, first. So the highest power we can have in terms of time is t to the first. All right? So let's take a look at this further. How does this fit? If I look here, there's no e to the h, t, so h is 0, e to the h t is 1. There's no frequencies associated with this input, so omega is 0. That wipes out sine, and I'm left with cosine is 0, which is a 1, which just leaves me with this kt term. So that's this piece down here. All right. And then if we take this, we have k0 plus k1t. Okay? So this will now be, this piece will be our particular solution. You go up to the highest order. So the input is t. We will have to go up to t to the first. And then this piece comes along for the ride. We have two parts. All right. So if you were to do this from scratch and didn't know it all ahead of time, you'd form the characteristic equation, solve. We have a root at -5, which isn't showing up too good. Darken that a little bit. All right. And so here we have what we said would be our particular. Y particular equals k0 plus k1t. So now we're going to substitute this into that and get our steady state response. So if we do that, take the derivative of this thing, we get this piece right here. 2yp dot is simply 2k1. So we take the derivative, that's all that's left. Plus 10 times this full thing in here equals the input. All right, we have when you break this down, we can get two equations and two unknowns. So if you take a look at the t term here, I can rewrite this, by the way, as 2t plus 0. I'll comment why I did that in a minute. So this doesn't have a t, that does. So now I have k1t equals 2t times 10 out here. So we get k1 is 2/10. All right, knowing k1, I can solve for the 0th term. 2k1 plus 10k0 equals 0. All right, substitute in k1, we get k0 equals minus 4 over 100. So now we just take those and substitute this in. And here's the forced response. Forced, c e to the minus 5t. This term's purpose, I'm just going to keep emphasizing this, takes us from our whatever initial condition we have to what our steady state response is. It's a link between them. It's transitory, takes us across these. All right. So from a forced response point of view, I ignore the initial condition because I'm just isolating the input. So y forced of 0 equals 0. I let t in this equation be 0, and I'm left with c, that just becomes a 1, minus 4 over 100, and I put 0 in here, and that wipes that out. So that tells me what c is. Okay, so now I have, from what I've done before, the initial condition response just comes, here's our complementary solution, so I can say let y of 0 equal 6, and I have the usual initial condition response. So this is kind of nice. You can solve for various inputs. Once you determine the response to the initial condition, you simply take the forced response plus the initial condition response is the total response. Okay? Or I'll note, we could have, when we solved for the forced response here, I put y of 0 equals 0. If I put a 6 in here, I would have gotten 6 4/10, and I could have done it all in one. Whichever way you want to go, all are fine. So that takes us to the end of this. We will be moving on to some more complicated systems.